Have you ever stopped to imagine what mysteries the universe holds in its vast, silent depths? Out there, beyond the edge of our perception, time itself slows, galaxies breathe, and the echoes of creation still hum through the fabric of space. So take a breath, let the rhythm of the cosmos cradle you like starlight over calm water, and let your thoughts drift free. Because tonight, we're not just looking up at the universe, we're drifting through it, one quiet revelation at a time. The universe might be far older than we've come to believe. Most of what we know points to an age of about 13.8 billion years, a figure born from the cosmic microwave background and the measured rate at which space itself expands. Yet, the cosmos doesn't always give us a single answer. Some ancient stars and galaxies appear to have existed longer than that number allows. Others suggest that perhaps the universe's expansion rate isn't constant, or that dark energy, the mysterious force driving that expansion, could be evolving over time. None of this has been settled, so most scientists still stand by that 13.8 billion year benchmark. But curiosity lingers. Could the universe truly be older? Did we overlook something profound? Maybe what we call the beginning wasn't the start at all, but merely one act in a longer, stranger cosmic drama. Across the galaxy, there are countless worlds with no suns to orbit. Not every planet belongs to a star. Some wander freely through interstellar space, cut loose from any system, drifting without light or warmth. These rogue planets may have started like any other world, only to be flung away by gravitational turbulence. Or they might have formed alone, like stars that never quite ignited. They are dark, frozen, and nearly invisible except when they briefly eclipse distant stars or emit a faint infrared glow. Astronomers believe there could be billions of them in our galaxy, perhaps outnumbering the stars themselves. Each one spins silently through the void, without dawn or dusk, just endless night pierced by the faint shimmer of distant suns. The universe may not be a one-way journey, but part of an eternal rhythm. The standard cosmological model describes a universe that began with a Big Bang and continues to expand indefinitely. But some theories tell a different story, one of cycles where everything expands, collapses, and begins again. In that vision, the cosmos doesn't fade into darkness or crush itself in finality, it bounces back. After reaching its limit, it implodes, then erupts once more into fresh creation. Each new universe carries faint echoes of the last, like a memory written into space-time itself. Speculative? Absolutely. Yet these ideas hint at a cosmos without a true beginning or end, but with an infinite heartbeat, pulsing across eons beyond comprehension. The oldest light we can see was born about 380,000 years after the Big Bang. Before that, the universe was a dense, glowing fog where light couldn't travel freely. As expansion cooled the chaos, atoms formed, the haze cleared, and photons finally escaped. That first light is the cosmic microwave background, the universe's own afterglow, still detectable today. Those photons have journeyed for more than 13 billion years, stretched by the swelling of space into faint microwaves. It's a whisper from the dawn of time, carrying the memory of when the universe first became transparent. Some stars host planets so exotic that they defy imagination. In certain systems rich in carbon, the pressures are so immense that entire planets could crystallize into diamond. Astronomers have found at least one world that fits the bill, orbiting a pulsar, the corpse of a dead star. Its density and composition suggest it's almost pure carbon in crystal form, a massive diamond world. It's far too hot to shine like a gem, but deep within, vast carbon lattices could stretch for thousands of kilometers. Such planets are rare, but they remind us of the universe's astonishing creativity, where a planet can be made of rock, gas, or even crystal. And then there's the shape of everything. The universe may have no edge, just infinite curvature. It's tempting to picture an outer boundary, some cosmic wall we might reach if we traveled far enough. But space doesn't behave that way. General relativity tells us that matter and energy define geometry, and current evidence suggests the universe is either infinite or so curved that it loops back on itself. In theory, if you traveled straight long enough, you might return to your starting point not by striking an edge, but by circling the curvature of space, much as sailors once circled Earth without ever finding an end. The universe may not be infinite in extent, but infinite in journey. Even our own sun may have a forgotten twin. Many stars are born in pairs, siblings from the same cloud of gas and dust. There's every reason to think our sun once had such a companion, born over 4 billion years ago. Whether it still exists somewhere out there, lost in the depths of the Milky Way, is a question that continues to remind us how much of our cosmic story remains unwritten. If such a sibling once existed, it would have long since wandered off, torn away by the gentle but relentless gravity of the Milky Way. Perhaps it still roams out there, tracing its own silent orbit around the galaxy, unseen and unreachable to us now. Some have even proposed that this hypothetical twin, often called nemesis, could be connected to mysterious extinction cycles on Earth, though we have no firm proof of that. Yet the notion lingers that our sun, steadfast and solitary in our sky, may once have shared its cradle with a companion now lost among the stars. A single droplet of neutron star matter would outweigh Mount Everest. Neutron stars are what remain when massive stars collapse after a supernova, leaving behind incredibly dense cores. They span only about 20 kilometers across, yet they pack more mass than our sun. Inside, matter is crushed so tightly that a teaspoon of it would weigh billions of tons. Imagine a raindrop of this material heavier than any mountain on Earth. That kind of density shatters everything we know about matter. Atoms are squeezed so closely together that electrons and protons combine into neutrons, forming an exotic superfluid of pure neutrons. Neutron stars are among the most extreme things in existence. Small, dark, heavy, and spinning at tremendous speed. In their immense density, they carry the memory of stellar death, where matter yields almost completely to gravity. Sometimes light itself bends under that same force. When it passes near regions of intense gravity, such as clusters of galaxies, the very fabric of space and time curves. This bending changes light's path, the way glass bends a ray through a lens. We call it gravitational lensing. It can produce multiple images of the same distant galaxy, stretched into arcs or rings across the sky. These are not multiple galaxies, just multiple routes that the same light has taken through warped space-time before arriving here. In rare instances, astronomers have even watched the same supernova appear to explode more than once as its light reached us along different gravitational paths. It's a quiet reminder that in this universe, even light can take a detour and still find its way home. The first stars may have blazed 1,000,000 times brighter than our Sunday. They were unlike anything that exists today, born from the pure hydrogen and helium left behind by the Big Bang. These so-called population 3 stars contain no metals at all, which made them enormous, hot, and short-lived. Some may have been hundreds of times the mass of our sun, burning through their fuel in mere millions of years before collapsing in brilliant explosions. None of them survive now, but their brief lives reshaped the cosmos. They forged the first heavy elements, filled galaxies with light, and set the stage for everything that came after, including us. Their light has faded, yet their legacy endures in the chemistry of ancient gas clouds and in the quiet scaffolding of the early universe. Dark matter flows through your body as you sleep. Even when you lie motionless, this invisible substance streams around you. It is not a mist or shadow, but a kind of matter that does not interact with light. It neither reflects nor emits nor absorbs it, but it has mass and responds to gravity. Our galaxy is wrapped in an enormous halo of dark matter, and as Earth moves through it, trillions of dark matter particles are believed to pass through every square centimeter of your body each second. They do not strike your atoms, they leave no mark, yet they are there, ghost-like and constant. Without them, galaxies would fall apart, structures would not form, and the universe as we know it could not exist. We still do not know what dark matter truly is, but we know this much. It is part of you slipping through you silently every moment of your life. Some galaxies glow without stars at all. In the far reaches of space, astronomers have found galaxies that shine faintly even though they hold few, if any, stars. These spectral structures contain mostly gas and dark matter, showing almost no sign of star formation. Some may have been stripped of stars through violent encounters. Others may have failed to form them in the first place. A few are visible only in special wavelengths, appearing as faint blurs in deep sky surveys. They challenge our understanding of how galaxies are born and evolve. If they are full of dark matter, why no stars? If they once had them, where did they go? These dim, drifting remnants move through space like fossils from another age, reminding us that not every galaxy blazes with light. Some wander unseen, silent witnesses to the deep history of the cosmos. And somewhere out there, in that same vastness, lies a cold patch of the universe that, by all accounts, should not even exist. In the faint afterglow of the Big Bang, known as the cosmic microwave background, there's a region in the sky that stands out. It's not just slightly cooler than the rest, it's dramatically colder and far larger than we ever expected such a feature to be. This enormous patch stretches across hundreds of millions of light years, defying the smooth and random distribution that early universe physics predicts. Some suggest it's the shadow of a massive cosmic void, a vast stretch of underdense space. Others imagine it could be something even more exotic, perhaps the scar of a collision between our universe and another during the brief, chaotic birth of cosmic inflation. No theory fully explains it yet. The cold spot lingers, quiet but haunting, a subtle reminder that the universe may still be hiding deeper truths about its origins. The moon, meanwhile, is slowly slipping away from us. Each year, it drifts a few centimeters farther, roughly the speed at which your fingernails grow. This retreat began about 4.5 billion years ago, when the moon first coalesced from debris near a much younger Earth. Back then, it was close enough that our days lasted only a few short hours. The culprit is tidal friction, the energy tug of war between Earth's oceans and the moon's gravity. As Earth spins, it drags those tides slightly ahead of the moon's pull, transferring a bit of energy that nudges the moon outward inch by inch. Over human lifetimes, it's imperceptible, but over eons, it reshapes the dance of our planet and its companion. One day, Earth and Moon may face each other permanently, locked in eternal symmetry. For now, the moon just keeps drifting, a patient traveler under our turning skies. In certain binary star systems, two stars orbit so closely they can touch, even share their outer layers like partners in a cosmic waltz. As they evolve, one may swell and pour its gases onto the other, creating a swirling bridge of matter between them. Sometimes it's a steady exchange, a quiet conversation of gravity and plasma. Other times, it erupts in bursts of light or ends in a spectacular merger. The physics is intricate, but the sight would be mesmerizing. Two suns entwined, one stripped bare to a brilliant core, the other bloated and luminous, both bound in destiny. From such intimate unions can emerge some of the universe's rarest phenomena, from powerful supernovae to neutron star pairs that warp space-time itself. Even stars, in their grandeur, can share, transform, and embrace. And though we call it the vacuum of space, it's anything but empty. Even in the darkest reaches between galaxies, quantum physics tells us that the void is alive with motion. Pairs of particles and antiparticles flicker into being, only to annihilate an instant later. This ceaseless activity forms a shimmering backdrop to all reality, influencing the behavior of fields, particles, and perhaps even the mysterious energy accelerating the universe's expansion. When we picture deep space as still and silent, we're only half right. Beneath that stillness hums a restless sea of possibility, where creation and destruction unfold endlessly just beneath the surface of nothing. And then there's time itself. We like to think it flows evenly, a constant beat shared by all things. But time bends to gravity, to motion, to the curvature of space-time. near massive objects like black holes, time slows relative to the cosmos beyond. This isn't conjecture, it's measured fact, verified by satellites and atomic clocks. Yet some wonder whether time might vary across the vast structure of the universe itself, shaped by how it expanded in its infancy. Could distant regions experience time differently, subtly out of sync with our own? It's a daring thought, but in a universe ruled by relativity, perhaps even time is fluid, stretching and folding as it moves through the grand geometry of existence. When we gaze upon the Milky Way, what meets the eye is a brilliant spiral of stars, gas, and dust, woven together into those graceful arms we find so familiar. Yet beyond that luminous disk lies something far grander, something our eyes cannot see, a vast halo stretching far past the galaxy's edge. This halo, a massive sphere of diffuse gas and dark matter, is a kind of invisible architecture surrounding everything we think of as the Milky Way. Within it drift ancient clusters, lonely stars, and an ocean of unseen mass, all bound together by gravity, shaped by countless collisions and mergers over cosmic time. We don't see it directly, but we sense its presence through the motion of stars and the bending of light. What we call the Milky Way is just the radiant core of a much greater structure, a glowing heart wrapped in unseen arms. We've managed to capture light from a galaxy that existed just 200 million years after the Big Bang. Think about that. The universe is about 13.8 billion years old, and that light has traveled across expanding space for more than 13.5 billion years to reach us. Because light doesn't move instantaneously, what we see is not the present but the deep past. Using the James Webb Space Telescope, astronomers identified that faint light stretched and slowed as space itself expanded. The galaxy is small, dim, primitive, but within its glow are clues to how the first cosmic structures took shape. Observing it is like peering through a narrow keyhole into the universe's infancy when darkness was first pierced by newborn stars. Now, if you were to map all the galaxies across the observable universe, you'd discover something stunning. They aren't scattered at random. They gather in vast filaments, connected like threads in a cosmic tapestry, with immense voids of emptiness in between. This grand pattern is called the cosmic web, an intricate structure stretching across billions of light years. And when you zoom out far enough, it begins to resemble something eerily familiar, a neural network, the kind inside your own brain. Dense clusters of galaxies act like neurons, the filaments like axons linking them together. Of course, the resemblance is visual, not functional. The universe isn't conscious. But it's a humbling beauty to realize that the largest structure in existence and the one that lets you think about it share such a haunting similarity. Even stars can sing, though not in the way you'd expect. Space is silent because there's no air to carry sound waves, but within stars, vibrations travel through their gaseous interiors like seismic waves through Earth. These oscillations make the star's surface pulse ever so slightly, and scientists detect them by measuring minute variations in brightness or motion. The field devoted to this is called astroseismology, the seismology of stars. Every star has its own unique pattern of vibrations, shaped by its size, structure, and age. By decoding those patterns, we peer beneath the surface, learning what's happening deep inside. It's like cosmic echolocation, listening to the music of the stars played across light years, a symphony too deep for human ears. And here's a thought that bends time itself. Some stars are older than the galaxies, they now call home. Galaxies grow over billions of years, merging, colliding, pulling in stray systems. So a star that once belonged to a smaller galaxy can now orbit inside a larger one formed through such mergers. These ancient suns are relics of earlier eras, witnesses to the building of cosmic cities, reminders that even galaxies are still under construction. Those ancient stars dwell on the outer edges, or gather in dense spherical clusters that circle far from a galaxy's heart. Some are more than 13 billion years old, nearly as ancient as the universe itself. They hold the chemical fingerprints of a cosmos still in its infancy, when only the simplest atoms existed and heavier elements had yet to be forged. These stars are fossils of light, silent witnesses from before the galaxy truly assembled. Their glow is ancient. Their stories began long before much of what we now see had even come to be. And then there are galaxies that seem to have lost the universe's invisible glue, dark matter. We think of dark matter as the unseen force that binds galaxies, explaining why their outer stars move faster than the visible mass suggests. Yet, astronomers have found galaxies that don't seem to play by that rule. Their stars move as though the invisible component is missing. The finding startled the scientific community because it doesn't fit neatly into our models. Some suspect collisions strip the dark matter away. Others think we still misunderstand what dark matter really is. Either way, these outliers whisper that the cosmos still guards its mysteries, that perhaps the laws we call universal are not so universal after all. The sun, too, has a rhythm. It rings like a vast resonant bell. Deep within, waves of pressure ripple through its plasma, bouncing between layers, setting the star into a constant, subtle vibration. These aren't the kinds of sounds our ears can hear. They are slow, deep pulses far below human hearing. Yet with the right instruments, scientists can detect them using this music of the sun to study its hidden interior. This science is called helioseismology, and through it we can map the sun's density, rotation, and secret flows of gas beneath its glowing surface. In this way, the sun becomes an instrument of cosmic music, intricate and unending. When we learn to listen, its melody tells us about stars everywhere. Across the universe, galaxies trace the outlines of immense invisible filaments. These are not made of stars or gas, but of dark matter, stretching across billions of years of cosmic history. Over time, dark matter formed this vast web, and galaxies gathered along its threads like pearls on a string. We can't see the filaments directly, but we detect their presence through how galaxies cluster and how light bends while passing through them. Some filaments span hundreds of millions of light years, linking colossal galaxy clusters while separating them with vast empty voids. This dark scaffolding shapes where galaxies form and how they move, yet we still don't know what dark matter actually is. The structure is immense, unseen, quietly holding the universe together. And then there's something even stranger. Space itself can stretch faster than light. No object can outrun light, but space isn't bound by that limit. Right after the Big Bang, space expanded so quickly that regions of the universe drifted apart faster than light could cross between them. This wasn't movement through space, it was the expansion of space itself. Even now, distant galaxies recede, not because they are moving fast through space, but because the space between us and them is stretching. If they're far enough away, that stretching carries them faster than light, placing them beyond our reach forever. It doesn't violate physics. It's simply how the cosmos behaves at the grandest scales, expanding not with haste but with steady, endless patience. Our own solar system rides this cosmic current in a spiral dance. We often picture planets orbiting the sun in flat, tidy circles, but zoom out and the picture changes. The sun itself is traveling around the Milky Way at nearly 1 million kilometers per hour, and as it moves, the planets follow, not just circling the sun, but spiraling behind it through space. The result is a helical path, like a corkscrew twisting through the galaxy. Everything moves. The planets, the sun, the stars, the galaxy itself. There is no stillness in space, only elegant, eternal motion. Even as we sleep, we drift in grand spirals through the galaxy, carried in layers of orbits within orbits, a cosmic dance so vast we never feel it. And even nothing, the pure void, has a temperature. If you venture far enough from stars, planets, and galaxies into the vast dark between them, you'll find yourself surrounded by what feels like pure nothingness. Yet even that nothingness isn't truly empty. because the vacuum has a temperature. About 2.7 Kelvin, just a whisper above absolute zero. That faint warmth comes from the cosmic microwave background, the ancient afterglow of the Big Bang, stretched thin and cooled over billions of years of cosmic expansion. This delicate radiation saturates every corner of the universe. Wherever you go, it's there. It's the silent thermal echo of our cosmic dawn, still humming faintly, still measurable, and as time drifts forward, that glow will cool even more. In a few trillion years, the cosmos may hover near absolute zero, but it will never reach it, because even in the emptiest expanse, the ghost of heat refuses to die. Quantum fluctuations may have sculpted everything we know. At the tiniest scales, far beneath atoms, the universe dances unpredictably. Tiny bursts of energy flicker in and out of existence, born from the uncertainty woven into quantum physics itself. Many cosmologists believe those fleeting fluctuations were stretched to cosmic proportions in the universe's first heartbeat during a brief moment called inflation. As space ballooned at impossible speed, those microscopic ripples were magnified into vast waves, seeding the great architecture of the cosmos. Matter gathered in those ripples, forming galaxies, stars, and everything in between. The grand structure we see today, the filaments, the voids, the galaxies, all may trace their origins to those primal tremors in the nothingness. Everything we know, born from the trembling of the void. Some stars, in their dying moments, throb like beating hearts across millennia. Not every star ends with a violent explosion. Some fade slowly, breathing in and out through rhythmic expansions and contractions. These are variable stars, their brightness waxing and waning in steady cycles. Some pulse in days, others take months or years. The cause lies in their outer layers, where gases expand, cool, then collapse and heat again. Astronomers use these celestial rhythms as cosmic yardsticks, since the timing of their pulses reveals their true brightness and distance. Even as they fade, these stars keep time not with ticking clocks, but with long, patient breaths. Our own solar system drifts inside a vast bubble of hot gas. If your eyes could see beyond visible light, you'd find we float in a glowing cavity called the local bubble, stretching hundreds of light years across. It was likely carved long ago by supernova explosions, whose shock waves swept up surrounding gas and left behind this low-density pocket. Now we move quietly within it, surrounded by a thin shell of hot gas and dust. It's not harmful, it's not even something we can sense, but it's real. A tranquil remnant of ancient violence, now part of the calm scenery of our galactic home. Beyond it lies something stranger still, a region known as the Great Attractor, a gravitational enigma pulling entire clusters of galaxies, including our own, slowly toward it. Yet behind this immense mass lies a deep emptiness called the dipole repeller, a vast cosmic void stretching hundreds of millions of light years, pushing galaxies away. Together, they create a cosmic tug of war, pulling us forward, pushing us back, shaping our local universe. It's a quiet reminder that in the cosmos, both presence and absence, gravity and emptiness, can steer the journey we take. And through it all, trillions of neutrinos stream through you right now, silent and unseen. They pour out of the sun from dying stars, even from the birth of the universe itself. They barely notice matter, passing straight through planets, through you, as if you weren't there. Deep underground, detectors catch a rare few, letting us glimpse their ghostly nature. But most pass unnoticed, moving near light speed, touching almost nothing. The universe, it seems, is always in motion, even when everything feels still. The most massive stars can collapse into black holes without a single burst of light. We tend to picture such endings as titanic explosions, grand supernovas lighting up the galaxy in one final act. Yet, for the heaviest stars, the finale unfolds in near silence. Their immense mass turns against them when fuel runs out, gravity takes full control, and the core collapses so swiftly, so completely, that even the outer layers plunge inward. No explosion follows, no luminous farewell, only a sudden vanishing act. Astronomers call this a direct collapse. In that instant, a star ceases to exist, leaving behind a black hole, silent, unseen, and infinitely dense. We have even watched stars fade from the sky, their light extinguished without a trace, as if the cosmos simply blinked. It's a sobering reminder that not every death in the universe arrives with fireworks. Some end as whispers swallowed by the dark. Galaxies, too, have their own choreography. They can orbit each other the way moons circle planets. Though we often imagine galaxies as solitary islands adrift in space, many dwell in clusters, interacting, dancing, even embracing. Our own Milky Way is surrounded by a retinue of smaller companions, the Large and Small Magellanic Clouds being the most prominent. These galaxies trace long, slow, elliptical paths around us, cosmic moons weaving through the night. Sometimes the gravitational pull of a larger galaxy draws out streams of stars from its partner, forming luminous arcs that stretch across millions of light years. Over time, a smaller galaxy might be absorbed completely. These cosmic ballets unfold over billions of years, graceful and vast, beyond human scale. Even in the silence of space, galaxies find companionship. Then there are the universe's brightest eruptions, born from collapsing magnetic stars. A rare event called a magnetar hypernova can outshine entire galaxies. A magnetar itself is a neutron star wrapped in a magnetic field trillions of times stronger than Earth's. When a massive star collapses and channels that magnetic energy outward in an instant, it releases a burst so powerful that it can outshine everything for a few seconds. Such events are thought to cause the long gamma ray bursts we detect across the cosmos, flashes so intense their light travels billions of years to reach us. In those moments, a single compact object, dense beyond comprehension, unleashes energy on a cosmic scale. Yet even that spectacle fades quickly into the void. When we look to the farthest reaches of the cosmos, we find the edge of what we can see, about 46 billion light years in every direction. That's not the edge of the universe, just the limit of visibility. The farthest distance light has had time to travel since the Big Bang. Beyond it, the universe almost certainly continues, but its light hasn't reached us. And in some regions, it never will, as the expansion of space carries them away faster than light itself. Our observable universe is like a luminous bubble of awareness within a far greater reality, an island of visibility adrift in an ocean we cannot yet perceive. Beyond that bubble, more galaxies, more stars, perhaps endlessly. And within those galaxies, some harbor black holes so powerful they sculpt light itself. When matter falls toward these giants, not all of it vanishes. Some gets caught in magnetic fields and flung outward in narrow, blazing jets of plasma. These streams travel at nearly the speed of light, slicing through intergalactic space, stretching for millions of light years. We detect them as faint radio beacons, colossal signatures of energy marking the reach of invisible forces. In that way, even darkness finds a way to speak through light. Galaxies, like these are known as radio galaxies, they're immense jets stretching across the cosmos, among the largest structures we've ever observed. There's something profoundly poetic about that. The most intense streams of energy erupt from places where even light struggles to escape, near black holes. It's as if the universe is whispering that even silence can carve its own signature. Somewhere out there, a star in our own galaxy refuses to follow the crowd. Most stars in the Milky Way orbit in unison, circling in the same direction as the galactic rotation. But there's at least one rebel, cataloged as H04375439, moving against the flow, a retrograde orbit cutting upstream like a cosmic salmon. Why does it do that? Maybe it was once part of a smaller galaxy that was swallowed by the Milky Way, carrying the momentum of that lost system. Or perhaps some massive encounter, a gravitational slingshot from a black hole or a dense star cluster, hurled it into defiance. However it happened, it reminds me that the cosmos doesn't demand conformity. Even in a galaxy governed by order, there are wanderers who choose another way. Now, consider this delightful oddity. The center of our galaxy smells, at least chemically, like raspberries and rum. I'm not kidding. When astronomers analyzed a dust cloud near the Milky Way's heart, they found ethyl formate, a molecule that on Earth gives raspberries their flavor and rum its aroma. Of course, space itself doesn't smell, there's no air to carry a scent, but these molecules tell us something extraordinary. Out there, between the stars, complex organic chemistry is at work. Alcohols, sugars, even precursors to amino acids drift silently through the dark. It's not life, but it's the chemistry from which life can spring. Space doesn't taste like fruit or liquor, but its ingredients are there, floating, waiting. And then there's our cosmic neighbor, the Andromeda Galaxy, heading straight for us. It's about 2.5 million light years away, but that distance is shrinking. In around 4 billion years, Andromeda and the Milky Way will merge. The process has already begun. Their vast halos of hot gas and dark matter are overlapping, like two clouds softly brushing together. The future collision won't be a cataclysmic crash, more of a slow dance. Stars will glide past one another with elegance, merging into a single, larger, elliptical galaxy. Some call it Milkometa, a fitting name for the new cosmic identity taking shape even now. It's a meeting written into the fabric of space-time, unfolding over billions of years. Meanwhile, a faint glow surrounds you, whether you notice it or not. Every inch of space, including where you're sitting, is bathed in the cosmic microwave background, the afterglow of the Big Bang. This light, released when the universe was about 380,000 years old, has been traveling ever since, stretched into microwaves by the universe's expansion. You can't see it or feel it, but sensitive instruments reveal it as a near uniform glow in every direction. It's the oldest light we can detect, a whisper from the universe's infancy still echoing through space-time. And then there are supernovae, those brilliant deaths of massive stars, lighting up galaxies with their final breath. But not all of them blaze. Some collapse in silence, what astronomers call failed supernovae. In these cases, the star's core implodes into a black hole, but the outer layers never explode outward. Instead, they fall back, feeding the darkness they cannot escape. Even in failure, the universe finds a way to transform, turning light into gravity's most mysterious creation. Every so often, we witness a star that seems steady and constant suddenly disappear. No explosion, no fading light, just gone. It's as if the universe itself decided to close a curtain with no warning. That kind of vanishing act points to a collapse, so complete that almost every bit of energy gets devoured. The chaos is still there, immense and violent, but hidden from view. It reminds me that not every cosmic ending comes with sound and fury. Some pass quietly into darkness. Deep inside the pull of gravity, whole galaxies exist that are mostly gas and dark matter. When we think of galaxies, we picture brilliant spirals or glowing ellipses filled with stars. But some galaxies barely shine at all. These faint structures contain very few stars, yet they hold mass, mostly as gas and dark matter. Ordinary telescopes struggle to find them. They show up as hazy patches or through indirect hints. Some might be galaxies that failed to fully form, perhaps losing their gas early on, or being heated before they could build many stars. Others might just be passing through temporary stages in their evolution. What they share is subtlety. No spirals, no fireworks, only quiet gravitational influence. They're reminders that not everything in the cosmos demands attention. Some things simply are. Black holes, too, have their moments of merging. Two of them can orbit each other, locked in a cosmic waltz, sending out ripples through space-time known as gravitational waves. As they lose energy, The dance tightens until they merge in a final silent crescendo. Two unseen giants becoming one. No light, no flare, but bursts of gravitational waves race outward, and we can now catch them here on Earth. The first was detected in 2015, a direct confirmation of what Einstein predicted a century earlier. Since then, we've caught dozens more. Each one carries a story, a record of immense collisions in faraway galaxies, long ago. These black hole unions are quiet, invisible, but unimaginably powerful, turning entire solar masses into waves that stretch the fabric of space itself. For a fleeting instant, space-time sings. Some stars end not with a bang, but with a slow fade, taking billions of years to dim. Smaller stars, like our own sun, go gently. After consuming their hydrogen, they swell into red giants, shedding outer layers into space. What's left behind is a dense, glowing ember called a white dwarf. It doesn't burn anymore, it just cools, slowly releasing the last of its stored heat. Over eons, it dims further, becoming what we call a black dwarf. But the universe isn't old enough yet for one to exist. Every white dwarf that's ever formed still glows faintly somewhere, fading quietly in the dark. The death of such stars feels less like a finale and more like a soft ember cooling through cosmic time. Time itself behaves differently near a black hole. According to Einstein's general relativity, gravity doesn't just pull, it bends the very fabric of space and time. The stronger the gravity, the slower time flows compared to regions with weaker gravity. Near a black hole, this effect becomes extreme. If you were orbiting just outside the event horizon, your minutes would pass as years for someone watching from far away. This isn't some sci-fi fantasy. It's a real measured phenomenon called gravitational time dilation. We've even observed mild versions of it using GPS satellites. But near black holes, it becomes profound. They don't just trap light, they stretch time itself. Between galaxies lies a darkness colder than any laboratory on Earth. Far from stars or planets or even dust, the intergalactic void reaches temperatures barely above absolute zero, about 2.7 Kelvin. That's colder than any place you could find naturally on our planet and beyond the reach of most human experiments. This chill exists because there's almost nothing there. No particles, no energy to hold warmth. Just the faint afterglow of the Big Bang whispering across space. These voids are vast and empty, spanning millions of light years. The quietest and loneliest realms we know, the deepest shadows of the cosmos, where only the echo of creation remains. As the universe ages, it grows ever more transparent. In the beginning, light couldn't travel freely. In the beginning, the cosmos was a blinding haze of energy, a sea of charged particles, where electrons and atomic nuclei danced freely, scattering light in every direction. But as the universe expanded and cooled, something remarkable happened. Electrons finally paired with nuclei to form neutral atoms. And just like that, light was freed to travel without obstruction. This great transition, called recombination, took place about 380,000 years after the Big Bang, releasing the faint afterglow we still measure today as the cosmic microwave background. From that moment on, the universe became ever more transparent. Galaxies and stars ignited, adding fresh sources of light, while matter thinned out, giving photons longer, clearer paths to wander. Over time, the darkness itself became see-through. Space, once glowing and dense, now allows light to drift across vast distances with almost nothing in its way. Then, we did something extraordinary. In 2019, using the Event Horizon Telescope, humanity captured the first direct image of a black hole, or rather, the silhouette it casts upon the glowing gas surrounding it. The black hole itself remains invisible, but its presence is betrayed by a ring of superheated material, swirling at near light speed. This one lies at the heart of galaxy M87, some 53 million light years away. What we saw was a nearly perfect circle of shadow, surrounded by light, bent and twisted by gravity. It took years of coordination, combining radio telescopes across the planet to form one virtual Earth-sized eye. The result was far more than a photograph. It was a quiet revolution in our understanding of reality, proof of one of nature's most extreme phenomena, not through imagination, but through light itself. And speaking of light, you can see a galaxy with nothing but your eyes. On clear, moonless nights in the northern hemisphere, look up and you might spot a faint oval blur in the sky. That's the Andromeda Galaxy, our nearest large neighbor, sitting about 2.5 million light years away. The light reaching your eyes tonight began its journey long before humans existed. Andromeda holds roughly 1 trillion stars, twice as many as our Milky Way, and it's slowly drifting toward us. Think about that. You can stand in your backyard, no telescope, no technology, and see an entire galaxy suspended in the dark. Something ancient and immense, quietly glowing across cosmic time. In 2015, a tiny instrument on Earth caught a whisper from the depths of space. The LIGO Observatory detected faint ripples in space-time itself, born from the collision of 2 black holes more than 1 billion light years away. These gravitational waves are unimaginably subtle, distorting the fabric of space by less than the width of a proton. Yet with precision engineering, we can hear them. LIGO and its partners serve as the universe's ears tuned to the low rumble of creation. That faint chirp confirmed what Einstein had predicted a century earlier, that massive events can send out waves through the very structure of reality. On this small blue planet, we caught the echo of invisible giants colliding far across the cosmos. But not everything is coming closer. The universe is expanding, and that expansion is speeding up. Some galaxies are retreating so fast that their light will never reach us, no matter how long we wait. They've crossed a boundary beyond which communication is forever cut off, slipping past the cosmic event horizon. As eons pass, more of the universe will fade from view. Not because it disappears, but because its light can no longer make the journey. The cosmos is growing, yes, but it's also gently erasing the view of itself. And then there are black holes older than stars. Most black holes form when massive stars collapse, but some may predate the first stars entirely. These primordial black holes could have formed in the earliest fractions of a second after the Big Bang, when tiny fluctuations in density caused gravity to squeeze matter into ultra-compact knots. Some might be minuscule, others may have grown over time. We haven't seen one directly, but if they exist, they might explain dark matter, seed the first galaxies, or reveal secrets of the infant universe. They would be ancient fossils, older than any star, silent witnesses from the first heartbeat of time itself. When I think about entangled particles, I imagine invisible bridges spanning the vastness of the cosmos. Quantum entanglement stands as one of the most baffling revelations of physics. 2 particles once linked remain bound in a way that defies our everyday sense of separation. Change one, and its partner responds instantly, no matter the distance between them. It doesn't mean they're sending messages faster than light, but it does whisper something profound, that the quantum world may be woven together in a deep, underlying unity. Some physicists propose that this entanglement could be part of the very fabric of space-time itself, perhaps even helping to hold it together. The particles born in the infancy of the universe might still share those connections today, stretched thin across the expanding cosmos. If that's true, then across the void there could be silent, unseen threads linking distant regions, faint quantum murmurs from the dawn of time, still echoing between galaxies. Now consider the vacuum of space, a place we call empty. Even there, quantum physics insists energy stirs. A perfect vacuum, free of atoms, particles, and radiation, still seethes with restless motion. Tiny fluctuations arise and vanish. Particles and antiparticles wink in and out of being. Fields tremble ever so slightly. This endless dance gives rise to what we call vacuum energy, a kind of pressure-filling space itself. On the grandest scales, it might help explain dark energy, the mysterious driver behind the universe's accelerating expansion. Unlike normal energy, vacuum energy doesn't thin out as the cosmos grows. It stays constant, pushing space apart faster and faster the more of it there is. It's an astonishing idea that the more nothingness we have, the more something it becomes. The silent force of empty space could be what's tearing the universe wider apart. Then there are black holes, those cosmic abysses, so dense that not even light escapes. Yet thanks to Stephen Hawking, we know they aren't completely mute. At the event horizon, where space bends beyond return, quantum effects come alive. Virtual particles form pairs, and occasionally one slips away while its partner falls in. The escaping one becomes real, stealing a sliver of the black hole's energy. Over unimaginable spans of time, this slow leakage causes the black hole to shrink and ultimately vanish. For one with the mass of our sun, that fade-out would take longer than 1 trillion years. It's the most patient kind of death imaginable. Not a grand explosion, but a quiet, gradual disappearance into nothing. Now, when we think of matter, we tend to picture solids, liquids, and gases, yet the universe prefers something else, plasma. Plasma is a gas so energized that its atoms split apart, freeing electrons from their nuclei. It's what stars are made of, what fills the solar wind, the interstellar medium, and even the vast spaces between galaxies. Most of the visible matter in existence is in this state. Plasma behaves unlike any other form, dancing with magnetic fields, flowing like a liquid, conducting electricity across unimaginable distances. On Earth, we glimpse it only in lightning, flames, or neon lights, but out there, it's everywhere, glowing, moving, shaping the structures we observe. And then there are gravitational waves. Gravity, it turns out, doesn't just pull, it ripples. When massive objects like black holes or neutron stars collide, they send vibrations through space-time itself. These waves stretch and squeeze space as they move, racing outward at light speed. For decades, we could only imagine them, but now, with exquisitely sensitive instruments, we can actually detect their faint whispers. Each wave carries a story, revealing how much mass was involved, how fast those titans spun, how deeply space-time bent. They make no sound our ears can hear, but they're real, subtle tremors in the cosmic fabric. And if we could step back far enough to map all the galaxies, we'd see they're not scattered randomly. They trace a vast, interconnected structure, the cosmic web. Galaxies cluster along invisible filaments of dark matter and gas that stretch like tendrils between enormous knots called superclusters. Between those lie enormous voids, almost empty. We can't view the web directly with a telescope, but large sky surveys reveal its form. It looks like a network, a foam, even a map of neurons in some colossal cosmic brain. The universe, on its grandest scales, isn't chaos dressed as order. It's a vast cosmic fabric, woven, not assembled, something that feels grown, organic. The James Webb Space Telescope can peer so deep that it captures galaxies long gone, their light still traveling through time. Webb was designed to see farther than any instrument before it, and because light takes time to reach us, looking far means looking back. The light from distant galaxies reveals them as they were billions of years ago. Some no longer exist in the forms we see. They may have merged, dimmed, or transformed entirely, but their ancient glow is still making its way here, an echo frozen mid-flight across space-time. That's one of astronomy's quiet paradoxes. Telescopes don't show us the present universe. They reveal a layered history of cosmic moments. Each deep field image is a slice of time, a gallery of extinct light. The most distant galaxies shine with photons that began their journey before Earth was born. When I gaze at a galaxy billions of light years away, I'm not just measuring distance, I'm witnessing age. That light began its voyage before the sun ignited, before the solar system even began to swirl into being. Some galaxies we see today cast off their light more than 10 billion years ago, light that has been stretched and thinned by the expansion of space itself before finding its way to our detectors. In a way, we're watching the deep past play out in the present. Many of those stars have long since burned out, yet their light remains a soft whisper across eternity, reminding us that the night sky holds stories older than our planet. Whole galaxies can vanish behind veils of cosmic dust. Even giants can hide. In certain regions, thick clouds of interstellar dust obscure what lies beyond. This isn't the dust you wipe from a shelf. It's made of carbon grains and silicates floating through cold molecular clouds. When a galaxy hides behind one of these clouds, its visible light is blocked. We only uncover it using special eyes tuned to infrared, radio, or X-ray light, which can slip through the dust. Astronomers have found entire galaxies this way, glowing behind what once seemed like empty sky. Space can deceive us. Darkness isn't always emptiness. Sometimes it's a secret waiting for the right kind of vision. And then there are galaxies framed by luminous circles where gravity itself bends light from something even farther away. When the alignment is precise, we see what Einstein predicted, a ring of warped light, an Einstein ring, perfect in symmetry, shaped not by motion but by gravity's geometry. This gravitational lensing turns mass into a cosmic lens, curving space-time and magnifying the background glow. Einstein rings are rare, delicate loops of distorted light, the result of perspective and physics intertwined. The light can come from a distant galaxy, a quasar, even a supernova. These cosmic mirages let astronomers weigh galaxies, trace dark matter, and peer into the universe's infancy. They're silent wonders, natural lenses, sculpted by the universe's own shape. And perhaps space itself is infinite. When I look up, I can't help but wonder, does it ever end? Is there an edge? Yet every observation points to an endless cosmos. No boundary, no center, just more galaxies, more stars, more space. We can only see the observable slice, but beyond it, the universe may go on forever. If that's true, most of it will forever lie beyond our reach. We'll never witness it all, no matter how far our instruments stretch or how long we wait. An infinite universe doesn't promise infinite possibilities, but it does offer endlessness, a calm vastness, expanding quietly without conclusion. Cosmic rays come crashing into Earth from the depths of space. Every single second, streams of high-energy particles known as cosmic rays bombard our planet. Some are born from the sun, others from distant reaches of our galaxy, and some may have traveled from realms beyond it. They are built from protons, atomic nuclei, and bits of matter flung across the universe at unimaginable speeds, accelerated by supernovae, black holes, or forces we've yet to name. Most of these travelers are turned away by Earth's magnetic field or swallowed by the atmosphere, yet a few make it all the way to the ground, and some even pass through you right now. Though they're mostly harmless, they remind us that space is never truly empty. It's filled with energy, motion, and unseen messengers carrying stories from events that happened light years ago. When a cosmic ray meets a detector, it's like hearing the echo of a supernova across time, the journey of a particle that began in an explosion and ended in your sky. When we talk about what came before the Big Bang, we step into strange territory. The phrase feels intuitive, but it might not mean anything at all. General relativity and many cosmological models tell us that time itself began with the Big Bang. That instant didn't just create matter and energy. It brought into being the fabric of space and the flow of time. To ask what existed before that is like asking what lies north of the North Pole. Some theories imagine a universe that came before ours, or a quantum state where time behaves unpredictably or doesn't exist in any recognizable sense. But in most scenarios, there is no before to explore, not even in imagination. The Big Bang wasn't an explosion in space, it was the birth of space itself. There was a time when astronomers mistook quasars for nearby stars. When they were first spotted, they looked like faint points of light indistinguishable from ordinary stars, but their light didn't follow the rules. Their spectra were bizarre, and their brightness changed in ways that puzzled scientists. Only after years of study did we realize these were not stars at all, but galaxies far away with intensely active hearts. At their centers spin supermassive black holes surrounded by disks of superheated gas spiraling inward. That gas glows so fiercely it can outshine every other star in its galaxy combined. The first quasars were so distant their light had been traveling for billions of years before reaching us, and yet, to our telescopes, they appeared as tiny stars, a beautiful mistake that led to one of astronomy's most illuminating discoveries. Even our own home in the cosmos is not stationary. The Milky Way, together with the Andromeda Galaxy and dozens of smaller companions, drifts through space as part of a cluster called the Local Group. And this group itself is on the move, drawn toward a massive gravitational anomaly known as the Great Attractor. Beyond that, deeper still, lies the Shapley supercluster and perhaps other massive regions still hidden by the dense plane of our own galaxy. These invisible giants tug at us, their presence felt through the motion of everything nearby. It's as though our entire cosmic neighborhood is sliding silently towards something vast and unseen. We can measure the pull, but we can't yet see what calls to us from the dark. At this moment, we exist in what I like to think of as the universe's stellar springtime. The cosmos around us glows with the birth and death of stars, each one a brief spark in an immense story. Yet this season of light is temporary. For hundreds of millions of years after the Big Bang, the universe knew only darkness. The first stars lit up that void, and with them began the slow evolution of everything we now see. Since then, the rate of star formation has risen, peaked, and begun its long decline. We live in a moment between abundance and quiet, a time when stars still form, but less often than before, and far more than will ever come again. Someday, the last stars will ignite, and after that, the universe will dim, its fires slowly fading. But today, we are still bathed in light. The cosmos still hums with creation, bright enough for wonder, calm enough for reflection. Star formation begins with clouds of cold hydrogen and helium, drawn together by gravity until they collapse into blazing spheres. Yet over the ages, that raw material grows scarce. It becomes trapped within stars, blown into space by supernova explosions, or heated so much it can no longer clump and cool. Given enough time, galaxies will exhaust their reserves, and no new stars will be born. Those that already shine will age, flicker, and fade. The blue giants will go first, then suns like ours, and finally the long-lived red dwarfs until even their dim embers cool into darkness. The universe won't flicker out in a single instant. It will dim slowly, gracefully, as if the cosmos itself were drifting into sleep. What remains will be black holes, white dwarfs, neutron stars, and the profound hush of a cold cosmos. Not a tragedy, simply stillness. Most of the universe is made of matter we cannot see. The brilliant stars, the glowing galaxies, the colorful nebulae we admire are only a sliver of what's actually there. The bulk of it does not shine or reflect. This unseen ingredient is called dark matter. Though we've never observed it directly, its fingerprints are undeniable. Galaxies rotate too fast for their visible mass. Light from distant galaxies bends more than it should. Clusters of galaxies cling together more tightly than gravity from visible matter alone could explain. All of this points to an invisible mass, over 5 times more abundant than ordinary matter. Dark matter pervades everything, sculpting the architecture of the cosmos, unseen but indispensable, the quiet scaffolding that holds the universe in place. Light from the first galaxies has been stretched thin by the expansion of the universe. When light journeys through space, it doesn't merely travel, it stretches. As the cosmos grows, it pulls light waves apart, lengthening them. The glow that once streamed from the earliest stars has shifted from visible light to the deep infrared. This stretching is called redshift, and it's how astronomers chart both distance and time. The more the light is stretched, the farther away and older its origin. With telescopes like James Webb, we can finally glimpse that ancient glow, faint and crimson, after billions of years on the road. What began as the youthful shimmer of newborn stars now reaches us as a faint echo, softened by the breath of an expanding universe. Some physicists have dared to ask if our universe might be a kind of projection, a three-dimensional image cast from a deeper two-dimensional reality. This concept, known as the holographic principle, emerges from the study of black holes, where the information about everything that falls in seems to be recorded on the event horizon rather than within the hole itself. It raises the possibility that the cosmos, too, could operate this way, that the depth and volume we experience are an emergent illusion born from information etched onto a distant boundary. It's not proven, and it won't change how you tie your shoes, but it reminds us that what we perceive as solid and real may, at its core, be stranger than we imagine. On the tiniest scales, space may not be smooth at all. To our eyes, it looks seamless, and even under a microscope, it seems empty and continuous. Yet some theories of quantum gravity suggest that space is made of minute, discrete elements, like pixels in an image or grains of sand forming a beach. This smallest possible scale is called the Planck length, about 10 to the minus 35th meters. Below that threshold, the smooth fabric of reality might unravel into a frothy, fluctuating texture. We don't yet possess the technology to probe it directly, but if this idea holds, then everything we know, stars, galaxies, even thought itself, unfolds within a universe structured down to its very foundation. Out there are stars that spin faster than the blades of your kitchen blender. Some whirl so furiously that their equators bulge and their surfaces blur into dizzying speed. Neutron stars, the ultra-dense corpses of massive suns, take this rotation to extremes. A kind known as millisecond pulsars can spin hundreds of times every second, entire city-sized spheres of nuclear matter rotating faster than any machine we could build. Their radiation sweeps across space like cosmic lighthouses, ticking with astonishing precision. Many of these pulsars orbit companion stars, stealing matter and momentum, spinning ever faster. They are among the most rapid rotators and the most reliable clocks in the universe, marking time silently as the cosmos continues its long, quiet fade into darkness. For a long time, cosmologists debated whether the universe might one day collapse upon itself, folding everything back into a final cosmic implosion. But the evidence we have now points toward a different destiny, one of unending expansion that slows but never stops. As galaxies drift farther apart and the birth of new stars dwindles, the night will grow ever darker. One by one, the remaining stars will exhaust their fuel and die, black holes will slowly evaporate, and even the very atoms of matter may decay. The universe will drift into a cold, silent emptiness we call heat death. It's not a sudden finale, but a slow fading of the cosmic symphony. Over trillions of years, energy will stretch thin, galaxies will unravel, and motion will give way to stillness. The end will not come as fire or as ice, but as silence. A universe that once sang itself into existence will quietly fade into its own echo. Some galaxies even exhale stars through immense cosmic winds. At the cores of certain galaxies, especially those lit by active black holes or bursting with star formation, powerful outflows erupt from the center, hurling gas, dust, and even infant stars into the vastness between galaxies. These superwinds can extend tens of thousands of light years, sweeping material far into intergalactic space. They're powered by radiation, magnetic forces, and the explosive energy of dying stars. Over eons, such winds can strip a galaxy of the gas it needs to make new stars, leaving it dim and red. Yet in doing so, they scatter heavy elements through the cosmos, seeding future generations of stars and worlds. In that sense, a galaxy breathes inhaling matter, creating life, and exhaling it back into the void. In the far future, the universe will resemble a dark, endless sea. Trillions of years from now, galaxies will have drifted so far apart that each one will stand alone in the darkness. No new stars will form. The old ones will burn out. Even the faint glow of white dwarfs will fade to black. What remains will be scattered remnants, black holes, and the dim residue of ancient light. Over incomprehensible timescales, even those black holes will evaporate, and matter itself may dissolve. All that will persist are faint particles moving slowly through infinite emptiness. This long, quiet decline is the heat death of the universe, not a sudden extinction, but a vast stillness, a cosmic ocean with no motion, no sound, and no shore. We might even live inside one of the great cosmic voids. The universe is not evenly filled with galaxies. It's a web of dense clusters separated by enormous empty regions called voids, spanning hundreds of millions of light years. Some scientists think our own galaxy may reside within one of these underdense regions. If so, that could help explain puzzling measurements, such as variations in the cosmic microwave background or the apparent rate of expansion. Living in a void doesn't affect our daily lives, but it reminds us that what seems like emptiness may actually be part of a larger cosmic bubble floating gently through an invisible gravitational sea. Then there are magnetars, neutron stars with magnetic fields so strong they defy imagination. A magnetar is the collapsed core of a massive star about the size of a city, yet containing more mass than our Sunday. Earth's magnetic field guides a compass, but a magnetar's could wipe data from thousands of miles away, distort atomic bonds, or tear matter apart. These fields don't last forever, slowly decaying over time, but while they endure, they unleash violent flares of high-energy radiation that can be detected across. No experiment on Earth could ever reproduce such power. They are among the most extreme objects known, dense and silent, shrouded in invisible force, like stars transformed into pure memory and magnetism. And then there's the largest known structure in the observable universe, a colossal formation of quasars. In 2013, astronomers found a chain of these bright galactic cores stretching over 4 billion light years. This enormous cluster, called a large quasar group, challenges the idea that the cosmos is uniform on the grandest scales. Our models predict that structures shouldn't grow beyond a certain size, yet this one exceeds that limit. It consists of dozens of quasars linked across vast cosmic distances, suggesting that the early universe may have formed more intricate patterns than we once believed. Whether it's a real connected structure or a coincidence of perspective remains uncertain, but its existence reminds us that the universe is both more complex and more connected than our theories can always explain. Black holes twist the very fabric of reality into a funnel where time itself seems to bend. They don't merely capture light, they reshape the structure of space-time. As I drift closer to the event horizon, space curves inward and time appears to slow. From afar, the seconds near the black hole seem to stretch endlessly until at the edge they almost freeze. This distortion forms a deep funnel in the geometry of the cosmos, steep, narrow, and one-way. Inside, every direction leads toward the singularity. The deeper I go, the more space and time swap their roles, with inward motion becoming a journey through time rather than space. There's no turning back. This is not a metaphor. It's geometry sculpted by gravity and written into the fabric of existence. There are corners of the universe that will never meet again. As the cosmos expands and accelerates, entire regions drift apart faster than light could ever bridge. Even if eternity waited, their light would never reach us. The same goes both ways. Some places are forever beyond our message, the space between stretching too fast to cross. Over billions of years, more of the universe will slip beyond the horizon of communication. Galaxies will stand alone, each an island in a dark, growing sea. Yet nothing here violates physics. No object outruns light. It's the fabric of space itself, expanding serenely, separating the cosmic archipelago piece by piece. The heaviest element born in a stellar explosion is gold. It's scarce not only on Earth but across the universe. Ordinary stars can't make it. Instead, gold is forged when neutron stars collide or in rare, violent supernovae. In those events, atomic nuclei are crushed together under unimaginable heat and pressure, creating heavy elements like gold, platinum, and uranium. These atoms are then scattered through space, mixed into clouds of gas that someday form stars, planets, and eventually us. Every ring, every tiny grain of gold dust carries the memory of a cosmic collision, a quiet relic of violence resting on your hand. Gold isn't just beautiful, it's ancient, stellar, and born from the universe's own alchemy of fire. As light travels through the ever-stretching space between galaxies, it too feels that expansion. When I observe light from distant galaxies, I'm looking back in time, and I see that light stretched by the space it crossed. As the universe expands, so does the path the light must take, lengthening its wavelength and shifting it toward the red. This is the cosmological redshift. The light doesn't slow or lose energy by colliding with anything. It's simply stretched as the universe grows. The cosmos literally pulls on the light, elongating its signal before it reaches us. So when I gaze at distant galaxies, I'm not just seeing distance or age, I'm witnessing the history of space itself, a quiet record of the universe's steady breathing. Echoes of ancient sound still linger in the structure of the cosmos. In the early universe, before atoms could form and light could roam freely, matter and radiation existed as a seething plasma. Within it, pressure and gravity danced together, creating ripples of compression and rarefaction, the universe's first sound waves. These waves left faint imprints on the density of matter, a frozen echo of that primordial music. Today, I can trace that echo in how galaxies are spaced, a preferred distance repeating across the sky, like a standing wave preserved through time. We call this baryon acoustic oscillation, a subtle but measurable signature, a fossil record of cosmic sound, still shaping everything we see. Galaxies, too, live, collide, and are consumed. On the vast timeline of cosmic evolution, they interact like slow dancers. When a small galaxy drifts too close to a giant, gravity tears it apart, its stars stretched into long, elegant streams that blend into the larger system until the smaller one disappears entirely. Around our own Milky Way, we can still find remnants of such feasts, stellar arcs curving across the night, once part of other galaxies. This process, called galactic cannibalism, unfolds gracefully, not violently, but inevitably. Through these slow meals, great galaxies grow, not by construction but by quiet assimilation, one galaxy melting into another, leaving behind only a ripple among the stars. And then there are stars that flicker like distant fireflies. Not every star shines steadily. Some pulse, some dim and flare again with perfect rhythm. Their changes come from pressure waves within eruptions on the surface, or orbiting companions casting shadows. From Earth, they seem to breathe gently, glowing and fading in celestial tempo. Some complete a cycle in mere hours, others in years, yet their rhythm is steady, reliable, like clocks written in starlight. Astronomers rely on these cosmic signals to chart distances that span the universe. A single rhythmic flash repeating itself across time can reveal how far a star truly lies and the measure of its intrinsic brightness. Stars don't simply burn. Some seem to inhale and exhale like living things. And not every black hole rests at the heart of a galaxy. Some drift alone, untethered. A black hole can be hurled away from its birthplace by gravity's chaos, flung from its home during a galactic collision, or propelled outward by the recoil of a merger. Once expelled, it becomes a solitary nomad gliding through interstellar or even intergalactic space, unseen and nearly undetectable. It shines no light unless it brushes through gas or disturbs nearby stars. Yet, somewhere out there, these dark wanderers drift quietly, unanchored, without orbit, without companion, without belonging. Only mass, motion, and the relentless gravity of a thing that fell inward and never cease falling. Even black holes, the most immovable objects we know, can be launched across galaxies. When two of them collide, their union shakes space-time itself, sending ripples of gravitational waves through the cosmos. But those waves don't always balance. When more energy surges in one direction, the newborn black hole gets a recoil, a gravitational kick, so fierce it can shoot away at thousands of kilometers per second. Some are exiled completely from their galaxies, doomed to wander the void between them. Others take up wide, erratic paths, roaming the dark. These exiled black holes are nearly invisible, but the math and the evidence whisper that they exist, silent travelers driven by the echo of their own creation. Even the universe's most steadfast giants can be shifted by the right kind of wave. Some stars, stripped to their cores, become spheres of pure carbon. When a star like our sun dies, it peels away its outer layers, leaving behind a dense remnant, a white dwarf, under enormous pressure that carbon core can crystallize. In essence, some stars become cosmic diamonds, the size of Earth but unimaginably dense, glowing faintly from their lingering heat. They no longer fuse atoms, yet they shimmer for billions of years before fading to black. Astronomers have even recorded subtle pulsations in some white dwarfs, vibrations like the ring of a distant bell, a quiet jewel cooling in the void, once a star, now a crystal forged from ancient fire. Most of the universe's story is still unwritten. 13.8 billion years may sound like forever, but if you picture the universe's entire timeline stretching trillions of years into the future, we're still standing near the dawn. Stars are still being born, galaxies still gathering, black holes still radiating with the energy of falling matter. Far ahead, the stars will dim, galaxies will drift apart, and the cosmos will fall into silence and cold. But that era hasn't arrived. We live in a luminous interval, a golden age when the universe is alive with energy and transformation. The past may be vast, but the future is greater still. The remains of supernovae continue to expand for millennia. When a massive star dies, it erupts in a supernova brighter than an entire galaxy. But that's just the beginning. The shockwave races outward for centuries, sweeping up gas and dust, shaping the universe as it goes. These expanding shells, called supernova remnants, glow across every wavelength, each pattern revealing the fingerprints of the explosion. Some form intricate threads, others roiling clouds. The Crab Nebula is one such relic, still stretching outward from a blast witnessed on Earth in 1054. Supernova remnants are like the long sighs of dead stars, unfolding long after the light itself has gone. Even a distant planet can twist the light of a star. We usually associate gravity's bending power with giants, stars, galaxies, or black holes. Yet even a planet can act as a lens. When a planet passes directly between a star and our telescopes, it magnifies the light slightly, an effect called micro-lensing. It's faint and rare, but powerful enough to uncover planets that no telescope could ever see, even beyond our galaxy. A flicker, a subtle curve in the light, and a hidden world announces its presence. The planet itself may be dark and cold, but its gravity whispers, "I'm here." Once the entire universe glowed a brilliant orange. In the early aftermath of the Big Bang, it was a searing plasma, radiating intense light. As it expanded and cooled, atoms formed, and light could finally move freely. At around 3,000 degrees Kelvin, the whole cosmos would have bathed in a warm orange hue. Not the deep black of today's night sky, but a soft glow filling every corner of existence. That ancient light has stretched with time into the faint microwave signal we detect today, the cosmic microwave background. But long ago, the universe truly glowed, a single ember fading slowly into the dark. Even now, not every part of the cosmos cools at the same rate. As it expands, the universe releases its heat gently, like an oven slowly shutting down. Yet, some regions dense with matter or light cling to warmth a little longer, holding on to the echoes of creation. Clusters of galaxies, for instance, are filled with scorching gas that manages to stay hot for billions of years, while other places out there cool much faster, left to drift in the cosmic chill. Those differences in temperature shape everything, from how galaxies take form to how stars live and die, to how long cosmic processes can sustain themselves. Even in a universe ruled by elegant and simple laws, there's always room for variation, little imperfections that give rise to warm patches, slow declines, and subtle pauses in the grand unfolding of time. The universe doesn't lose its heat like a machine shutting down. It cools more like weather, irregular, full of texture, quietly alive in its own rhythm. One day, we might even witness the emergence of another universe. Some cosmological models hint that new universes might bud off from our own, born through quantum fluctuations, black holes, or other cosmic mechanisms that remain beyond our understanding. If that were to occur, it would likely happen in some unreachable expanse, far outside any instrument's sight. Yet, in principle, we might someday detect the signs, an expanding bubble of new physics breaking away from everything familiar. We can't tell if it has ever happened before, and we can't say if it ever will, but the thought persists that somewhere, sometime, in the silent darkness of space, a new beginning could be waiting to be born. A start hidden within an ending, a whisper nested in silence. The cosmos still vibrates from its birth cry. In that first fraction of a second after the Big Bang, space itself ballooned outward in a dramatic surge we call inflation. That burst stretched out minute quantum fluctuations, turning them into ripples, the seeds of everything that would follow: galaxies, stars, planets, and all the light that fills the sky. Those same ripples left behind faint traces, echoes that we can still observe today in the cosmic microwave background as subtle temperature differences, and maybe one day we'll detect their rhythm in the form of primordial gravitational waves, the faintest trembling woven into the fabric of space-time. The universe may appear silent now, but it still carries that memory, like a bell that keeps ringing long after the strike. The cosmos is vast, and through you, it has found a way to know itself. Of all the facts in astronomy, this one might be the most moving. You are made of stardust. The carbon in your cells, the calcium in your bones, the iron coursing through your blood, all were born in stars, scattered across the void, and gathered again into you. You are not apart from the universe. You are its way of becoming aware, a brief flare of consciousness in a cosmos that otherwise only expands, burns, and cools. In that sense, the universe has given itself eyes, and through those eyes, it looks back, reflects, dreams, and even as you drift towards sleep, it continues to dream. Thank you for traveling through the cosmos with me. Together, we've crossed immense distances past fading stars and newborn galaxies, listened to ripples in space-time and echoes from the dawn of creation. And somewhere in that vastness, among the ancient light, the quiet between galaxies and the shimmer of dust, there was you, breathing softly, mind unwinding, maybe already asleep. The universe moves with energy and mystery, yet it holds stillness, too. It contains fire and gravity, but also peace. And the fact that we can experience that peace, piece by piece, through calm and through wonder, is something profoundly beautiful. So wherever you are, whether fully awake or drifting past thought, may your dreams tonight be kind. May your body rest like starlight upon water. and may you carry within you the quiet glow of a universe that shines not just above, but within. If you're still awake, feel free to explore the next chapter. And if you'd rather float into sleep with stories like this, softly told and filled with wonder, stay with me. There's always more to discover, one dreamer at a time. Good night.